All right, hello everyone, and welcome to our sixth lesson of Unit 4, which is on the Introduction to Titration. Today, your understanding is that a substance that changes into a new substance, or when its properties change, no mass is lost or gained. Today's objective is to identify the equivalence point in a titration based on the amounts of the titrant and analyte, assuming the titration reaction goes to completion. Before we talk about titrations, we need to make sure we understand how acids and bases behave when they react with each other. In the Bronsted-Lowry model, an acid is a proton donor and a base is a proton acceptor. Remember when we say proton, we're talking about an H plus ion. That's because a hydrogen is just one proton and one electron, but when we make an H plus ion, remember we've lost an electron, which means now we are only left with a proton. In the example shown, water is acting as the acid because it donates a proton to ammonia. Ammonia is acting as the base because it accepts that proton. Once the acid donates the proton, it becomes what we call the conjugate base. And once the base accepts the proton, it becomes the conjugate acid. So in this reaction, water is donating the proton and it becomes OH minus, the conjugate base. And NH3 accepts the proton and it becomes NH4 plus, the conjugate acid. This conjugate acid-base relationship is important in titrations because titrations rely on the controlled transfer of protons to determine how much acid or base is present. So let's identify the acid, base, conjugate acid, and conjugate base in each of the following reactions. Remember, your acid is your proton donor and your base is your proton acceptor. So for me, it's a lot easier to identify the components of an acid-base neutralization if I know and identify the conjugate acid-base pairs. So what I mean by that is if I'm looking at H2SO4, its conjugate acid-base pair is going to be the product that's only differing by a proton. So that would be this HSO4 minus. So as you can see, it lost a hydrogen when it became a product, which means it was a proton donor. So I know this is my acid, and this is my conjugate base. Now, by default, that would make our other pair the base and the conjugate acid, but let's look at it. So we can see, again, they're only differing by one proton, but this accepted a proton, which means this is our base, and this is our conjugate acid. Now let's do the same thing with our bottom reaction. Again, I like to identify the acid-base pairs, which only differ by a proton. So we can see NH3 accepted a hydrogen plus ion, so that's going to be a base. And that turned into the conjugate acid. So then looking at our other acid-base pair, again, only differing by a proton, we can see that this one lost an H plus ion or donated that proton. So this is going to be our acid, and this will be our conjugate base. So now that we understand the basic idea of acid-base neutralization reactions, let's talk about what a titration actually is. So this is an analytical technique that lets us determine the concentration of an unknown solution, which we call the analyte. And to figure out the concentration of the analyte, we react it with a solution of known concentration, which we call the titrant. So the titrant is the concentration that is known in the reaction, and the analyte is the unknown concentration that we're trying to figure out. In the setup you see here on the left, the titrant is placed in the burette, and we control how much titrant is added drop by drop. The analyte goes into the Erlenmeyer flask at the bottom, often with an indicator that helps us see when the reaction is complete. So to summarize, your titrant is your known concentration in the burette, and your analyte is your unknown concentration in the flask. All right, so let's talk about what happens at the particle level when we neutralize a strong acid with a strong base. So here we have hydrochloric acid and sodium hydroxide forming sodium chloride and water. So to further understand that, let's break this apart into our complete ionic equation. So because we have a strong acid and a strong base, those are going to fully dissociate in water. So we have those ions separated from each other. And then sodium chloride is a soluble ionic solid. So when placed in water, it will fully dissociate. So as you can see here, what we're really looking at during the titration is our H plus ions reacting with our OH minus ions to form water molecules. So for simplicity in this particle diagram, I'm going to use 6 H plus ions. And for each quote unquote drop of base that I'm putting into my acid, that's going to be 1 hydroxide ion. So in this example, I have my acid as my unknown concentration. So this is going to be my analyte that is in the Erlenmeyer flask. And as you can tell, we have H plus ions, which means this is a very acidic solution right now as it sits. So our pH is going to start out very low, like let's say at a pH of 3. So right now with no base added, it's at a pH of 3. Now, as we start adding in our hydroxide, the hydroxides are going to mix with the H plus ions to form water molecules. So as we add our first OH minus drop of base, it's going to react with one of those H plus ions to form water. So now one of our H plus ions have reacted with a hydroxide ion to form water, which means now our pH went from 3 to something like 3.7. Because remember, water is neutral. So now as we're adding water, we're getting closer to a pH of 7. So now let's add another drop of base or another hydroxide ion. And again, let's add another drop of base or another hydroxide ion. So this is something we call the half equivalence point, where half of our moles of unknown have turned into our desired product, which in this case is water. So now we keep adding our base or hydroxide ions until all of the H plus ions have been neutralized to water. So now we had exactly 6 moles of H plus ions react with exactly 6 moles of OH minus ions to form 6 moles of water. So now all of our acid has been neutralized, and now we have a neutral solution with a pH of 7 with just water. Now this is what is known as the equivalence point. So our moles of acid equal our moles of base. Now in a titration, this would also be your endpoint, or when the indicator changed color. Now typically you are going to over titrate or keep adding in your base, and when that happens, your pH is going to continue to rise, because now as you add in your OH minus ions, they are not reacting with anything anymore. And we know when we have a concentration of OH minus increasing, that is an increase of base, which is going to increase our pH. So if we were to measure the pH of this solution, it would be much higher at like 8.5 or 9. So let's look at what we just talked about in terms of a titration curve, which we see on the right here. So here we have our pH. Remember, our pH started at about 3. and our equivalence point was at 7 or neutral. And then when we kept adding our base, we were at like 8.5. So we can see here that when we start measuring the pH of our solution, it's starting at that low number because all we have in there is acid. And as we start adding our base, the pH is getting closer and closer to 7 until we reach our equivalence point where our moles of acid equal our moles of base. So at that point, we would have water, which would be a pH of 7. So the most accurate way to determine whether you have reached your equivalence point is to actually have a pH meter calculating the pH of your solution the entire time. Then you can actually plot that titration curve that we focused on the last slide and find your equivalence point. However, when we are doing titrations in the lab, we usually use some sort of indicator that is going to change color when that equivalence point has occurred. So typically in our lab, we will be using phenolphthalein, which turns a light pink color at endpoint, which is going to give us a very close measurement of our equivalence point. Let's walk through the steps of how a titration is actually performed in the lab. First, we fill the burette with the titrant, which is the solution with a known concentration. Make sure to record its concentration and the starting volume in the burette. Next, we measure a known volume of our analyte, which is the solution with unknown concentration, and we're going to place it in an Erlenmeyer flask. Then to that analyte in the Erlenmeyer flask, we're going to add a few drops of indicator. The indicator is what is going to help us see when the reaction is complete or at its equivalence point. At this point, you're going to slowly add the titrant from the burette into the analyte while stirring constantly. We keep doing this until we see the indicator change color. Then you're going to record how much titrant was used, and that is going to help you solve for your concentration of analyte. Now remember, the equivalence point is the moment when the moles of titrant added equal the moles of analyte. This is the true chemical completion of the reaction. The endpoint is the color change that shows that we are at or very close to the equivalence point. So the indicator just helps us detect that equivalence point, and our goal is to stop adding titrant right when the faint color first appears, not after it gets dark. Now that we know that the equivalence point is where the moles of acid equal the moles of base, we can use that idea to do calculations to actually solve for the unknown concentration of our analyte. So we know from the past that when we're solving for concentration, it's moles over liters. So if we were to convert that into moles, it would be the concentration times the volume in liters. So if we know moles of acid equals our moles of base, that means we know that the concentration of our acid times the volume of our acid equals the concentration of our base times the volume of our base. Now this is for a 1-to-1 ratio, like what we did in our previous example of hydrochloric acid and sodium hydroxide. We had a 1-to-1 ratio of H plus to OH minus. Now if we were to do something like with hydrochloric acid, which is 1 H plus ion, and calcium hydroxide, which is 2 OH minus ions, that would just mean that we would need to multiply this side by 2 to keep the ratios the same. So let's do an example of titration calculations. So we have 25 milliliters of a 0.1 molar sodium hydroxide it's required to neutralize 15 milliliters of our solution of hydrochloric acid. So we can see we do not know the concentration of hydrochloric acid. So this is going to be our analyte that is in the Erlenmeyer flask, and sodium hydroxide is our titrant that's in the burette. So what it's saying is that we needed 25 milliliters from the burette in order to neutralize 15 milliliters of our acid that's in the flask. So in order to solve for the concentration of the acid, we use that equation MaVa equals MbVb. So we know our concentration of sodium hydroxide is 0.1 molar, and our volume is 0.025 liters. And we know our volume of the acid, which was 0.015 liters. And by calculating this, we will get our concentration of the acid. And then looking at sig figs, 25.00 is 4 sig figs, 0.100 is 3 sig figs, and 15.00 is 4 sig figs. So since our lowest amount of sig figs is 3, our answer needs to be in 3 sig figs. So that would be 0.167 concentration of HCl, and that would be our final answer. All right, let's do that again, but with a ratio that is not 1:1. So here we have concentration of calcium hydroxide solution, which is 2 hydroxide ions, with HCl, which is 1 H plus ion. So when we do our calculations with MaVa equals MbVb, we just need to have this one multiplied by 2 because we have 2 hydroxides per 1 hydrogen ion. So let's go ahead and figure out what we are actually doing in this titration. So our known concentration is HCl. So HCl is going to be our titrant in this situation, which is in the burette. And then calcium hydroxide is our analyte, which is in the Erlenmeyer flask. So into the Erlenmeyer flask, they put 30 milliliters of our analyte. And in order to neutralize that analyte, they needed to use 10 milliliters of our 0.02 molar hydrochloric acid. So when we're solving for this, we're going to be solving for the concentration of base. So we have our concentration of acid, which is 0.02. We have our volume at 0.01. And then our volume of base would be 0.03 times 2, so it's going to be 0.06. So our lowest number of sig figs is 3 from 10.0, so our concentration would be 0.00333 molar CaOH2. And you can either leave it like that or you could put it in scientific notation at 3.33 times 10 to the negative third concentration of CaOH2. So to summarize this lesson, please know the terms titrant and analyte and where those are found. The titrant is going to be found in the burette. The analyte will be in the Erlenmeyer. Your equivalence point is where your moles of acid equal your moles of base. Your endpoint is the actual observable signal that the equivalence point has been met, or color change with indicator. Just remember that titration is a key experimental technique used to determine the concentration of a solution by reacting it with a measured amount of a solution with a known concentration. And understanding and mastering titration is going to require both accurate measurement skills as well as a clear understanding of what is actually happening at the particle level. Have a great day. Bye.